Okay, so the natural question we have when we first come across covariance, definition of covariance, and where it comes from is in terms of when we're calculating variances of sums of random variables, is why is there an extra term in there? And the reason is because, well, we can illustrate this through what we call the Pythagorean theorem. For standard deviation. So you've probably heard of the Pythagorean theorem for, well, just the Pythagorean theorem in I don't know, from first grade or whenever they teach that, has to do with the lengths of the square of the sides of a triangle. And there's some intuition for that with random variables as well. So a key fact a fact that I won't prove here is that if we have two random variables, x and y, that are independent, then if x and y are independent, then covariance is 0. Terminology we use here is to say that x and y are uncorrelated. So what is the Pythagorean theorem? Well, the Pythagorean theorem tells us that if x and y are independent, then the variance of x plus y is the sum of the variances of x and y, because in this formula up here, this covariance term will be 0 because they're independent, and we'll just have the sums of the two variances. Right? So this holds, in fact, as long as the covariance is 0. And so the way to think about this is that the covariance being 0 corresponds to this perpendicular. So in a right triangle, right? In a right triangle, this is how we think of it, is that two random variables are independent if they're in some sense pointing in different directions. They're not, and pointing in orthogonal directions. They're not, information about one does not tell us information about the other, right? Whereas if we had a random variable, for example, where they were pretty well correlated, or where they had correlation, so let's say this was x and this was y, then this sigma x plus y, that distance there is actually quite a bit smaller, right, than we would get if they were at a right angle. So these have a covariance, and we have to take into account that covariance, how they vary, so that if they vary together, we have to change their we have to adjust the variance of the sum accordingly, right? So, for example, if every time x is very large and positive, y is very large and negative, then they would have a negative covariance. And even though X is very large, and Y is very large in the negative direction, they might have very large variances in their own right, but they kind of offset each other, right? So they kind of cancel out. The covariance is going to cancel that out for us. Okay, so that's something that we have to account for. So in general, if collection of random variables are pairwise uncorrelated, then the standard deviation of some linear combination of those random variables is the square root. So we take the values Cn squared times the variances, and then we add them up, we get the square root. And then in general, we also have, regardless if they're not uncorrelated, the variance of the sum of a linear combination is we have a variance term and then we have covariance term. Sum over all I less than j, ci, cj, covariance of xi, xj. All right, so that's covariance. Again, we'll come into covariance a bit more in when we deal with joint distributions. But before we do that, I do want to, before we move on, I do want to at least record some properties of covariance, and I'll do that in the next video.